Okay, we continue our discussion. We were talking about the link budget, particularly the power part of it. We will discuss about the noise much later. So, we have seen that we transmit the power from a source and which may have some gain. So, the transmitted power and the gain put together, we termed it as a effective isotropic radiated power, and when the gain is maximum in that direction at a distance r and with a receive antenna whose effective aperture or gain is known. So, we have calculated the receive power, and we have described it as that because of the distance there is some sort of a reduction of the power. So, though it is not attenuative loss, we still call it a loss because it is a reduction of power, and that loss is due to the path length. So, we termed it as a path loss. But then we were further discussing that the power received may be reduced due to other practical reasons. Those will be listed as other losses, and in that other losses we have discussed about the antenna depointing, because if the transmit antenna and receive antenna are both sides are not aligned properly, any one of them or both of them if they are misaligned. So, based on the misalignment there will be some losses because the antenna gain is not constant over complete theta or complete phi. And then we tried some model and estimate for a small deviation, small angle of depointing, what should be that depointing loss. And subsequently we have discussed about that the power which is transmitted from the transmitter amplifier to the antenna which is radiating. There are certain cables, connectors, bends, adapters, etc. may come, which may introduce some sort of a loss, which we termed it as a feeder loss. Now, let us go into the other type of losses. Now, the power is transmitted from the antenna and it is being received at the receiver, and in case of the satellite communication which is communicating between earth and satellite, there is a medium which is coming in. So, let us try to draw very briefly, let us call it earth with a north this side and equator, let us say here, and there is a location where our small antenna is put, and there is a satellite high up in the orbit which may be geosynchronous. This is the satellite. Satellite also has the antenna facing the earth. It is rotating in geostationary or geosynchronous orbit around the equator. Depending on this location, the distance or path we have calculated earlier, this is r. But then in between, near the earth, there is that atmosphere which has troposphere, and higher up there are ionosphere. Subsequently, there will be no gas or no particles, which will be free space. Though this distance is much larger, this troposphere and ionosphere may contain certain particles. At ionosphere there are electrons, we can call it a particle for the time being, electrons and ions, and that electromagnetic wave will interact with them. Similarly, at the troposphere there will be water vapor, water droplets, ice, dust, many particles may be there, and that also will interact with electromagnetic wave. So, this electromagnetic wave may be the input which is coming, and the output which will come out of the medium will be less, and this is due to the electromagnetic energy is absorbed by some of the particle, it may be scattered by the some of the particle. So, because of that, what is happening is some loss, is some attenuation. So, EM energy is attenuated. Generally, we call in atmosphere, and this attenuation is depends on the frequency of operation. We will discuss in detail about this when we talk in our propagation medium. Right now, we will just assume that there is certain attenuation which depends on the frequency, and this loss, this is loss in atmosphere, we termed it as a L atmos. So, there is a loss. That loss will depend on frequency, it may be large, it may be small, those things we will discuss detail, but there is atmospheric loss. What are the other losses that can come? That we have very briefly talked about something called polarization. So, there is a polarization loss, that is, if there is a transmit polarization, the transmitter E field vector, let us say it is vertically polarized, and the receive antenna polarization is not properly properly adjusted. So, it may have certain angle. This is transmit polarization, this is receive antenna polarization. So, because of that there will be mismatch of this wave plane, will have some loss. It is called polarization loss. And in some of the books it says that it is of the order of -20 cos of theta. Theta is the angle between these two planes. So, we will term it as a L polarization. This is termed as a L polarization. With all these losses, then that can be grouped together, and let us see how the expression then becomes. We have P r, which is equal to EIRP PT into GT, and at the transmit side we have loss due to transmit feeder, then loss due to transmit antenna pointing, then we have the medium which is coming between. So, and the medium, there is the path distance. So, there is a loss due to path, then loss due to atmosphere, and then we have the receiver where the receive antenna comes into picture, and we are assuming that GT is max and GR is also max, that is bore side value will take, and then there is a loss due to receive feeder, then loss due to receive antenna pointing, then there is a loss due to polarization. This is the transmit side, this is the medium, this is the receive side. Now, in all these losses, we know that the path distance is quite large. So, loss due to path is much more, or path loss is much more than all other losses put together. These are much smaller, you can consider, but it is comparatively smaller. So, in short, now we can write that P r is equal to P t G t into G r into 1 by loss of due to path and 1 by loss due to others. In dB term, the whole thing can be written as P r is equal to EIRP, this is EIRP, then plus GR this is in dB, minus loss due to path, that is path loss, minus loss due to others. Now, this whole thing people sometimes you can see in dB terms it is only addition or subtraction. So, if these numbers are properly calculated, you can draw a power level diagram. It may be like this, that is we have the transmitter power amplifier, and then there is some loss, that is feeder loss, then there is the transmit antenna, and then at a distance we have a receive antenna, and then there is a feeder loss, and then it goes to receiver. So, we can say that this is PT, and at this point, because it is loss due to transmit feeder, so this will be PT minus loss due to feeder. At this point, let us draw. At this point, there are other losses which are coming, and gain is also coming. So, here it is antenna, transmit antenna gain, and then there are losses due to transmitter pointing. So, at this point we can say it is PT minus L feeder plus GT, which is GT max, minus L transmitter point. Now, before it reaches the receive antenna, we have the loss due to path and loss due to path and loss due to atmosphere. So, that can be adjusted. So, we can say PT minus loss due to transmit feeder plus GT max minus loss due to transmit pointing minus loss due to path minus loss due to atmosphere. And then here we have antenna gain, that is GR, and the loss due to receiver pointing and loss due to polarization. So, those things can be listed, that is PT minus loss due to transmit feeder plus GT minus loss due to transmit pointing minus loss due to path minus loss due to atmosphere plus GR minus loss due to receive pointing minus loss due to polarization. And then after that, the further loss, that is loss due to receive feeder, the whole thing. So, the receive power is equal to PR will be PT minus L transmit feeder plus GT minus L transmit pointing minus loss due to path minus loss due to atmosphere plus GR minus loss due to receive antenna pointing minus loss due to polarization minus loss due to receive feeder. A diagram can be drawn that is based on these numbers, and these vertical lines could be the power in dB. So, you can see how it is varying and it is going. This is engineers sometimes draw this diagram, so that it comes clearly that where the losses are increasing or decreasing if it is in a pictorial form or graphical form. The other is there already, expressions are already available, they can be calculated also, from that also it can be found. So, with this let us go from the power to the noise. Before that, okay, we will try to give you certain assignments, and in the assignments some of the sums that will come will try to see that how the antenna diameter, as I said, that path loss is quite large. So, if you go on changing the receive antenna diameter, how much is the effect on the transmit antenna diameter if I take the downlink, that is satellite antenna. The other way is also true. Those things are in the problems. So, now let us go into the another part of the subject, which is called the noise power. Just now what we covered is the signal part of the power. Now, we will go into the noise part of the power. This is very important. This noise power is quite critical, and actually it sets threshold for minimum detectable signal. It sets threshold for the minimum detectable signal for the receiver. The receiver will have certain capacity to detect the signal out of noise. So, the noise level, that determines what will be the minimum detectable signal. Now, the receivers will have the receiver output will have contains the input noise plus noise generated in receiver. We will see into the detail. And the noise, it is a random process. Noise is a random process. Means mainly in most of the components and in the medium also. Let us say electrons are vibrating and changing their position based on the temperature. It gets excited, and because of that electron movement, there is certain kinetic energy creates certain voltage, which depends on the temperature, which may happen in the medium or in the component itself. So, this noise is very important for us to know, but in communication and radar, this reduction in, I should say, residual noise, there will be some noise always, residual noise is desired, whereas there are other systems which is called radiometer or in radio astronomy. Which actually measures the noise level. So, there has to be that just to distinguish input noise from locally generated noise. The input noise is what is important for the radiometer and radio astronomy. Anyway, we are interested in reduction of residual noise, or just try to understand how the noise comes into picture. Let us say, let us take an example that there is an amplifier. There is a power input and power output. This particular subsystem has a gain G. So, generally we say that power output is equal to G times the power input. The assumption is it is a deterministic and it is a linear process. But if we look at the antenna, the amplifier characteristics, it goes linearly and then it saturates. But this linearly does not start at 0. This is the base noise or floor noise. This is a term which is used. That means, at Pi is equal to 0, when there is no input, Po is, as per this expression, Po is supposed to be 0 for a finite gain, but Po is not equal to 0. There is some value here, and that is the noise which is generated inside the amplifier. Now, let us look at it in more detail, how it comes and how it can be measured, the value can be estimated. Let us take a resistance. This is resistance R at a temperature T degree Kelvin. Now, the electrons inside this resistance, because of the temperature which is non-zero, it will have certain random movements and it will have certain kinetic energy. That kinetic energy will be proportional to the temperature T. As we increase the T, that random movements are much more. So, it generates a random voltage across terminal, and that voltage, if we try to draw with time, this is V n. That average V n, the mean value is 0, but there is a V n RMS value which is given by, if you remember in our physics course, it is V n square, that is a Planck black body radiation, which is V n square is equal to 4 into h f b r by exponential e to the power h f by k t minus 1. Now, there are a lot of constants and other things. Let us list it. Let us list it separately. Let us say, again let us repeat, V n square is equal to 4 h f b r by e to the power h f by k t minus 1, where h is the Planck's constant, its value is 6.626 into 10 to the power minus 34 joule second. K is the Boltzmann constant, 1.38 into 10 to the power minus 23 joule per Kelvin. B is the bandwidth in hertz, careful, look at the units carefully. F is the center frequency of the bandwidth in hertz, T is the temperature in degree Kelvin, and R is the resistance in ohm. Now, if we put into Taylor series the denominator part, let us say e to the power h f by k t, it is 1 plus h f by k t plus half of h f by k t square plus like that. Now, at a higher frequency, let us say for microwave frequency, f is equal to 100 gigahertz, and let us say T is equal to 100 degree Kelvin. The value of h f is 6.6 into 10 to the power minus 23, and value of k t is 1.4 into 10 to the power minus 21. So, that means h f is smaller than k t. So, higher terms can be neglected. So, therefore, we can say e to the power h f by k t minus 1 is equal to h f by k t. Since the time is over, we stop here. We will continue the discussion in the next period.